Alright, so now after that review and after some new stuff, we can finally get into the down and dirty chemistry of it. We've been discussing the kinetic molecular theory, which says that all substances are made of small particles in constant random motion. But now we're going to start asking this question: what are these particles that we're talking about? What exactly is stuff made of? We don't want to just stop at the word particle and say, yeah, everything's made of particles, of small particles. We want to be good scientists and ask, well, what are these particles? How do they work? How can we describe them? How can we model them? How do they interact? So here's my temporary answer. These particles that we're talking about are atoms that sometimes join together to form larger structures. So the idea is that if we were looking at a water drop in a cloud or something, if we were to zoom way into it, it would be composed of water particles, just like you've seen me draw. But now we're saying that those particles are actually atoms, and atoms can join together to form larger structures. And as we will see, the atom itself is actually made of smaller little bits. So that's what we're going to get into now. What are atoms? How do they work? How do they join together to form larger structures? What are the atoms themselves made of? What are these tiny particles that make up everything? What are those particles made of? So the answer that I gave earlier was that all particles are atoms or atoms that have joined together to form larger structures. So here I have some examples. This is a picture, a diagram of an atom. We will look at this in more detail. It turns out that the atom is composed of smaller bits. So here's an atom, and then here's two different examples of different structures that atoms can join together to make. This is what is known as an ionic crystal. You guys will actually study this later this unit. The ionic crystal is composed of large numbers of particles of atoms, sodium Na and chlorine Cl, that have been kind of joined together, stuck together in a very orderly arrangement. Does anyone know what the substance is, by the way? NaCl is known as salt, so this would be a salt crystal. Over here, we see other atoms that have joined in a different arrangement. Instead of making one large structure, here I have multiple units. So there's one, here's one, here's one. I have all these units. These are known as molecules. We will talk about this later. And what if I told you that every red circle you see is an oxygen atom, and every white circle you see is a hydrogen atom? Would you know what this substance is? H2O, two hydrogens in a molecule, one oxygen in a molecule. There's my molecule. It's this unit of atoms stuck together. Yeah, this would be water. So these are different ways that atoms can come together to form molecules or to form ionic crystals that we will discuss. These are what I'm talking about when I'm talking about particles. Everything is made of particles in constant random motion. Those particles could be atoms, or they could be molecules, like water molecules, or they could be ionic crystals, like salt. So let's talk about how to classify these particles, how to classify matter. Well, first of all, we need to maybe define what matter even is. Matter is basically all the stuff of the universe, anything that has mass and takes up space. So anything that has mass and takes up space, you guys know a lot of this already. The measurement of how much space something occupies is known as volume. So really we can say that matter is anything that has mass and that has volume. Well, let me skip down here to this word density. Density is a ratio of mass to volume. So we could simplify this definition of matter and say that it is really anything that has density, which once again is pretty much everything except for light or except for energy. Energy is not matter. Energy is an idea that doesn't have mass or take up space. So yeah, we can classify pretty much the whole universe into energy and matter. And now we're looking at matter. Matter has mass, takes up space, it has mass and volume, it has density. Mass is a measurement of stuff. I know this seems like a really silly, simplistic definition, but it's the best I can do for now. Measurement of how much stuff is in a substance. Notice I did not say the weight. Where does weight come from? We talked about this already. Weight comes from gravity pulling down on something, right? So if you're floating around in interstellar space and there's no planets, no object around you to exert a gravitational attractive force, you won't have weight, but you will still have mass. You're still made of stuff. And then volume is a measurement of how much space something occupies, how much three-dimensional space. And like I said, both of these ideas, mass and volume, can be collapsed into the idea of density. Density is a ratio of mass over volume. D equals m over v. Very, very simple. Here is an example of why density is kind of an interesting idea. Here I have a bunch of different substances. This is a cube made of copper, Cu. This is a cube made of lead, iron, tin, zinc, aluminum. These are all elements. And then this one is bronze, which is actually a mixture of metals. If we were to zoom in here, we would see different types of atoms stuck together. Copper, lead, iron, tin, zinc, and aluminum are all elements, and then bronze is a mixture. So these are all the exact same size, so they all have the same volume, right? Volume of a cube is given as the length times the width times the height. It's a three-dimensional measurement, right? So how long is it? Back and forth. How tall is it? Up and down. And then how wide is it? Left and right. 3 dimensions to go into giving volume. So if I were to measure the volume of these, I don't know what the volume is. Let's say that each side of this cube is 1 centimeter. 1 centimeter times 1 centimeter times 1 centimeter. Maybe the volume would be 1 centimeter cubed. It's a cubic measurement. Why is it centimeters cubed? Because once again, the length, 1 centimeter, times the width, 1 centimeter, times the height, 1 centimeter. That's a cubic unit. Centimeters times centimeters would be centimeters squared. That would give me the area of one surface. Then I multiply that by one more dimension, one more centimeter measurement, and I get centimeters cubed. So volume is always how much three-dimensional space an object occupies. Anyway, even though these all have the same volume, they're going to have very different masses. Why? Because these substances, copper, lead, iron, tin, zinc, aluminum, and bronze, they all have different densities. I will tell you that lead is the most dense out of all of these. So what would we expect if we were to pick up the lead cube and compare it maybe to the aluminum or the tin cube? And those two are some of the least dense here. Yeah, the lead would have much bigger mass. It would weigh more in our hands on planet Earth. So density is important for the properties of substances. Iron is very dense. Remember, density is mass over volume. Per unit volume, it has a lot of mass. So it has more massive particles shoved into the same amount of space. Mass over volume, density. It's a very, very helpful way of classifying matter because it is what we call an intrinsic property. That means it depends only on the identity of the substance, not on size or shape of sample. So density, the density of lead, as long as the substance I'm analyzing is lead, the density will always be the same. It does not matter what the size of my sample is, what the mass of the sample is, doesn't matter the shape of the sample. If I calculate the density for lead, I'm always going to get the exact same number. It's an intrinsic property. It only depends on the identity. Lead always has a specific density. Copper has a different specific density. Iron has a different specific density, etc., etc. It does not matter the size or the shape of the sample that you're analyzing. As long as it is that substance, it's going to have a specific density. The density of lead, for example, the density of lead's abbreviation is Pb, by the way. The density of lead is 11.34 grams per cubic centimeter. That is very, very dense. The density of water is defined as 1 gram per cubic centimeter. So this has a density of about 11 times that of water. What would the density be of a cube of lead that was twice this big? It'd be the exact same number. What if I cut this cube in half and measured the density of only half of it? What would the density be? It'd be exactly this number. Density is an intrinsic property. So we can use it to classify and determine the identity of different substances. We can classify all the matter in the universe into these different categories. Matter can first of all be classified as a pure substance or as a mixture. We've kind of already gone over this. A pure substance is one type of element, so one type of atom, or one type of combination of atoms. We call the combination of atoms a compound. So earlier when I was talking about answering the question, what are these particles that we're talking about? All matter is made of particles and constant random motion. What are the particles? We said that there are atoms, there are molecules, there are ionic crystals. We could have referred to this single atom as an element. We will talk about that later. I'll give you a definition for element in a bit. Turns out it's going to be a specific type of atom. So there's a specific type of atom. And then both of these I could classify as compounds. How do I know that? Because they are multiple types of atoms compounded together, stuck together with what we refer to as strong chemical bonds. That's what all these bars represent. That's what these bars represent here. So elements and compounds. If you are analyzing a substance and it is composed of only one type of element, one type of atom, it's going to be a pure substance, an element. If you're analyzing a substance and it's composed of multiple elements or multiple atoms stuck together in a specific way and nothing else, it's going to be a compound. So this would be a compound of water. This would be a compound of salt. What would this be classified as? Well, I have compounds, I have water, I have H2O throughout, and then I have atoms or elements, don't I? So this would be a mixture. It's not a pure substance because it's not purely water, or it's not purely chlorine or purely sodium. It's a mixture of compounds and elements. Now, wait a second. Why, though, would this not be classified as a mixture? Is this not a mixture of chlorine and sodium atoms? Well, technically speaking, I guess you could use the word mixture, but that's not the best word. Why not? Because these are not loosely associated. They are strongly associated. They're stuck together with strong chemical bonds all throughout. So no, this is not a mixture. This is a compound. What about this? Could this not be classified as a mixture of oxygen and hydrogen atoms? Well, I guess it is true that I have oxygen and hydrogen mixed together here, but they're more than just mixed. They are strongly bound together. I have strong chemical bonds holding them together into one unit, into a molecule. So no, these would not be mixtures. These would be compounds. However, if I took my salt and I added it to the water, then I would have a mixture, which is what this is getting at. This is a mixture of compounds, of water compounds, and of elements of chlorine and sodium. This is a mixture of elements and different types of compounds. Are you guys with me? So one element or one type of compound would be a pure substance. If you have multiple things mixed together, so in this picture, here's an element mixed with a compound, that's a mixture. Mixtures can be classified as homogeneous or heterogeneous depending on their composition. So this word homogeneous, homo means the same, so it basically means it has the same composition throughout. It's very, very well and evenly mixed together. For example, if I were to grab a sample of this substance from here and a sample of this substance from down here, I would end up with the exact same proportion of things. It's the exact same. I get one orange element and one green compound. One orange element, one green compound. It's pretty well thoroughly mixed. However, here, a heterogeneous mixture, if I were to take a sample down here and a sample up here, those samples would be completely different. That prefix hetero means different. So this has a different composition throughout. It is not evenly mixed together.